All right, let's talk about something that sounds like magic. What if I told you that you could count millions, or heck, even billions of unique things using just a few kilobytes of memory? It sounds impossible, right? Well, today, we're pulling back the curtain on hyperloglog, the brilliant algorithm that does exactly that.
I mean, think about it. This is a huge problem for any big system. Let's say you're running a website and you want to know how many unique people visited today. The simple way is to just keep a list of every single user ID. But if you have millions of visitors, that list is going to eat up your server's memory, and fast.
And this is where you hit a fork in the road. On one side, you have your traditional methods, like a hash set. And yeah, they give you a perfect 100% exact count. But the cost? Massive memory usage that just keeps growing and growing. And on the other side, you've got hyperloglog. It uses a tiny, fixed amount of memory, and in exchange, it gives you an answer that's like 98 or 99% accurate. A pretty amazing trade-off, right?
When you're dealing with data at the scale of, say, Google BigQuery or Redis, getting an exact count isn't just expensive, it's basically impossible. The sheer number of items creates a total memory nightmare. You have to find a smarter way to do it.
Seriously, do the math for a second. If you've got a billion unique items, and each ID takes just 8 bytes of storage, you're already talking about 8 gigabytes of RAM. For one counter. That's just completely unsustainable. There has to be a better way.
So this is where hyperloglog comes into the picture. And you gotta understand, it's not really a counter in the way you'd normally think. It's more like an incredibly clever probabilistic estimator. It makes a highly educated guess, and it does it with stunning efficiency. So the official definition is that a hyperloglog, or HLL for short, is a probabilistic algorithm. Its whole job is to approximate the cardinality, which is just a fancy way of saying the number of unique items, in a huge data set, all while using a ridiculously small and totally predictable amount of memory. And this quote just nails the philosophy behind it. For most big applications, knowing you have about 100 million users is just as useful as knowing you have exactly 100,023,456. That tiny bit of imprecision is such a small price to pay for the incredible gains you get in speed and memory savings.
Okay, so how in the world does this trick actually work? Don't worry, we're not going to dive into a bunch of complex math. Instead, let's use a really simple analogy. Let's talk about mailboxes.
Just picture a long row of mailboxes in your mind, maybe 1,000 of them or so. These mailboxes are basically the algorithm's memory. We call them registers. Now, every time a new item shows up, like a new user ID, we're going to give it a special, unique ticket. And the magic really happens in these 4 simple steps. First, we take our item and hash it. That just turns it into a long, random-looking string of ones and zeros. That's our ticket. Second, we look at the first few bits of that ticket to decide which mailbox to go to. Third, we look at the rest of the ticket and count how many zeros there are right at the beginning. And here's the key, 4th step. We tell that mailbox to remember our count, but, and this is crucial, only if it's the highest number of leading zeros that mailbox has ever seen. So here's the big aha moment. Getting a random hash that starts with 1 0, that's pretty common. It's a 50-50 chance. 2 zeros, a little less common. But getting a hash that starts with, say, 10 zeros in a row, that is incredibly rare. So if one of our mailboxes says, hey, I saw a ticket with 10 leading zeros, that's a huge statistical clue. It tells us we must have processed a ton of items just to get that lucky. Okay, so we've run all our data through this process. Now we have a bunch of mailboxes, and each one is holding just one number, the biggest leading zero count it ever saw. So, how do we get from that to our final count of unique items? This is where the math gets a little bit clever, but the concept is simple. We don't need to get lost in the weeds. The algorithm just takes all those numbers from the mailboxes and averages them together using a special formula called the harmonic mean. And the reason it uses that specific average is that it's really good at smoothing things out and ignoring weird outliers, which gives us a really solid first estimate. But it's even smarter than that. Hyperloglog actually has built-in correction systems. If the count looks like it's going to be really small and a lot of the mailboxes are still empty, it actually switches to a different, more accurate counting method for small numbers. And if the count gets absolutely massive, it applies another little correction to account for the tiny, tiny chance that 2 different items might get the same hash ticket. So what's really cool about all this is that you are in control. With hyperloglog, you get to decide. You make the call on that trade-off between how much memory you're willing to give up and just how accurate you need that final number to be.
And this table just lays it out perfectly. The number of mailboxes or registers is what you get to choose. And just look at this. With about 1 kilobyte of memory, which is nothing, you can get an error rate of around 3%. Not bad at all. But if you can spare just 12 kilobytes, you can slash that error down to less than 1%. It's just a fantastic deal.
So what does this all mean in practice? Well, there's a simple rule of thumb here. If you want to cut your error rate in half, in other words, to double your accuracy, you just need to use 4 times the memory, or 4 times as many mailboxes. It's a very predictable relationship.
Now, it's also really important to know where HLL fits into the grand scheme of things. It answers one specific question. Roughly, how many unique things are in this giant pile? That's different from a Bloom filter, which answers, is this one specific thing possibly in the pile? And that's also different from a count min sketch, which estimates, how many times have I seen this thing? They're all different tools for different jobs.
And finally, let's just touch on performance. Adding a new item to a hyperlog structure is blazingly fast. It's what we call constant time, or O of 1. It doesn't matter if you have 10 items or 10 billion. Adding one more takes the same amount of time. Getting the final estimate is super quick too. It's just proportional to the number of mailboxes you chose. The whole thing is just beautifully simple and efficient.
So at the end of the day, the big takeaway here is that sometimes a good enough answer, right now, is infinitely more valuable than a perfect answer that's going to take too long or cost way too much. Hyperlog really shows us the power of smart approximation. It turns problems that seem impossible because of their sheer scale into something totally manageable. And that leaves us with a final question for you. What impossible problem out there could you solve with a clever guess?